A 3-digit number in base 10 will have either 4 digits or 3 digits in base 8. Let's start with the 4-digit number in base 8 since it's going to be larger, and then we'll work our way down. Let's see if we can find an upper limit on our 4-digit base 8 number by finding the maximum 3-digit number in base 10, which is 999, and convert that to base 8. We'll do that using the remainder method by dividing this repeatedly by 8 and pulling out the remainders, which will become the digits of our number. First, we'll divide 999 by 8. Our quotient is 124 with a remainder of 7. This means in base 8, 7 is going to be in the units digit because it's not part of this multiple of 8. Then we divide by 8 again. 124 is 8 times 15 with a remainder of 4. 4 is the remainder when we divide by 64, so it comes in next. We'll divide 15 by 8 again, and our remainder is 7. So 7 is our next digit. That's the remainder when we divide by 8 cubed. And then our coefficient of 8 cubed is 1, so that goes in our leftmost digit. This tells us that if our 3-digit palindrome in base 10, when converted to base 8, will have a maximum of 1 in this leftmost digit. This means C is equal to 1, and so our palindrome is 1DD1 in base 8, if this number exists. Now let's do casework on the value of A, starting with its maximum value with A equals 9. Let's write our 3-digit palindrome in base 10 in terms of its digits and combine like terms. Our 4-digit palindrome in base 8 will be 513 plus 72 times D, where D are these two middle digits. Since these two palindromes are equal to each other, we'll set these two expressions equal to each other. Since we're doing casework on A, we'll collect the other two terms on one side. To maximize our palindrome, we'll start with A equals 9. Simplifying, we get this expression. B and D are positive integers. This first term is even, and our sum is even, which means that B is even. Let's further narrow it down by finding the mod 9 residual of both sides. This gives us B equals 0. When we substitute, we get 36D equals 198. Dividing by 9, we get 4D is equal to 22, which does not have an integer solution for D, so we can discard this. Let's go on to A equals 8. On the left-hand side, we have the sum of two even numbers, and on the right-hand side, this is going to be odd. And we can see straight away that for A, an even number, we're not going to have a solution. So now we'll stick to odd A, and we'll go on to A equals 7. And we'll simplify. Our multiples of 5 are going to end in either 5 or 0. And here again, we have that B is odd because our sum on the right-hand side is odd. So this second term is going to end in 5, which means we're looking for a multiple of 36 that ends in 2. When we subtract this odd multiple of 5, we're going to get a units digit of 7. We'll get a units digit of 2 when D is equal to 7 or 2. Let's try 7 first because it's bigger. As predicted, when we combine the numbers, we get a multiple of 5. But unfortunately, B ends up being a 2-digit number, so it's not a valid solution. We'll try D equals 2. Solving for B, we find that B is negative and also not valid. We'll go on to the next odd value of A, which is A equals 5. 505 minus 513. Rearranging the terms, we get 10B minus 72D is 8. By inspection, we see that a solution is B equals 8 and D equals 1. So our base 10 number is 585. In base 8, that's 1111. And this is our answer. If you'd like me to solve any other contest problems, please leave them in the comments.